Welcome to this comprehensive presentation on key NLP techniques for text analysis. In the next 20 minutes, we'll explore the fundamental methods that power modern natural language processing. From basic text preprocessing to advanced deep learning approaches, we'll cover each technique with practical examples and real-world applications. Whether you're new to NLP or looking to deepen your understanding, this presentation will provide you with a solid foundation in text analysis techniques. Let's start with text preprocessing, the foundation of all NLP tasks. Text preprocessing involves several crucial steps to clean and prepare raw text for analysis. Tokenization breaks text into individual words or tokens. Stop word removal eliminates common words like the, is, and, at, that carry little meaning. Stemming and lemmatization reduce words to their root forms. Stemming chops off endings crudely, while lemmatization uses dictionary knowledge to find the actual root. Lowercasing and normalization ensure consistency, while removing punctuation and handling special characters clean the data. For example, the sentence, "The quick brown foxes jumped," would be tokenized into words, have stop words removed, and be lemmatized to "quick brown fox jump." Bag of words is one of the simplest yet powerful text representation techniques. It works by counting the frequency of each word in a document and creating a vector where each dimension represents a word's frequency. This approach is highly interpretable. You can easily see which words appear most often. However, it completely ignores word order, so dog bites man and man bites dog would have the same representation. The resulting vectors can be very high-dimensional, especially with large vocabularies, but both serves as an excellent baseline for text classification tasks. For instance, the text cat dog cat would be represented as a vector 2, 1 for the words cat, dog, showing that cat appears twice and dog appears once. TF-IDF, or term frequency inverse document frequency, improves upon bag of words by weighting words based on their importance. It combines two metrics: term frequency, which measures how often a word appears in a document, and inverse document frequency, which measures how rare the word is across all documents. This combination gives higher scores to words that are frequent in a specific document but rare across the entire corpus. For example, common words like the appear frequently but have low IDF scores, resulting in low TF-IDF weights. In contrast, domain-specific terms that appear often in certain documents but rarely elsewhere receive high TF-IDF scores, making them more informative for classification and analysis tasks. Word embeddings revolutionized NLP by capturing semantic meaning in dense vector representations. Unlike sparse bag of words vectors, word embeddings represent words as continuous vectors in a high-dimensional space, typically 100 to 300 dimensions. Techniques like Word2Vec, which includes CBOW and skipgram architectures, learn these representations by predicting words from context or vice versa. GloVe uses global co-occurrence statistics, while fast text incorporates subword information to handle out-of-vocabulary words. The magic of word embeddings lies in their ability to capture semantic relationships. Similar words have similar vectors, and you can perform vector arithmetic like king, man plus woman approximately equals queen, demonstrating that the model understands gender relationships. Contextual embeddings take word representations to the next level by generating dynamic vectors based on surrounding context. Unlike static word embeddings where bank always has the same vector, contextual embeddings like BERT, GPT, and Elmo generate different representations for the same word depending on context. BERT uses a bidirectional approach to consider both left and right context, making it powerful for understanding nuanced meanings. GPT uses an autoregressive approach, excelling at text generation tasks. Elmo provides contextualized word vectors that can be plugged into existing models. This context-aware understanding allows models to distinguish between river bank and money bank, capturing the polysemous nature of language and achieving state-of-the-art performance on many NLP tasks. Named entity recognition is a crucial NLP technique for identifying and classifying named entities in text into predefined categories. Common entity types include persons, locations, organizations, dates, times, and monetary amounts. Modern NER systems use sequence labeling approaches, often based on BERT or similar transformer models, to assign entity tags to each word in a sentence. This technique is essential for information extraction, enabling systems to automatically identify key entities in unstructured text. For example, in the sentence, Apple CEO Tim Cook visited New York, an NER system would identify Apple as an organization, Tim Cook as a person, and New York as a location, providing structured information from unstructured text. Part of speech tagging assigns grammatical categories to words, helping machines understand sentence structure and syntax. Common POS tags include nouns, verbs, adjectives, adverbs, prepositions, and more. Traditional approaches used hidden Markov models, but modern systems employ neural networks for higher accuracy. POS tagging is fundamental for syntactic parsing, which analyzes sentence structure, and for many downstream NLP tasks like machine translation and information extraction. For example, tagging the sentence, "The quick brown fox jumps" would identify the as a determiner, quick, and brown as adjectives, fox as a noun, and jumps as a verb, providing a grammatical blueprint of the sentence. Sentiment analysis determines the emotional tone, attitude, and opinions expressed in text. It ranges from simple positive, negative, neutral classification to fine-grained emotion detection and aspect-based sentiment analysis. Modern approaches use machine learning models, particularly deep learning with contextual embeddings, to capture nuanced emotional expressions. This technique has widespread business applications, from analyzing customer reviews and social media sentiment to monitoring brand reputation and improving customer service. For instance, analyzing the review, "This product is amazing. The battery life is incredible, but the price is too high," would not only identify overall positive sentiment but also aspect-specific sentiments, positive for battery life and negative for price. Topic modeling automatically discovers hidden thematic structures in large collections of text documents without prior labeling. The most common approach is latent Dirichlet allocation, which assumes documents are mixtures of topics and topics are distributions over words. Non-negative matrix factorization is another popular technique that factorizes the document term matrix into topic and document matrices. Topic modeling is invaluable for content summarization, trend analysis, document clustering, and understanding large text corpora. For example, analyzing thousands of news articles might reveal topics like politics, sports, technology, and entertainment, with each document assigned to one or more topics based on its content. Text classification is one of the most fundamental and widely used NLP tasks, involving the assignment of predefined categories to text documents. Applications include spam detection, news categorization, intent recognition in chatbots, language identification, and content moderation. Modern approaches range from traditional machine learning algorithms like naive Bayes and SVM to deep learning models using word embeddings and contextual representations. Multi-label classification allows documents to belong to multiple categories simultaneously. For example, an email classifier might categorize "win free money now" as spam with 98% probability, while a news classifier might assign both technology and business categories to an article about a tech company's earnings report. Machine translation automatically converts text from one language to another, enabling cross-lingual communication and access to information. Modern neural machine translation systems use sequence-to-sequence models with attention mechanisms, particularly the transformer architecture that revolutionized the field. These systems learn to align words and phrases between languages and generate fluent translations in the target language. Multilingual systems can translate between multiple language pairs using a single model, and real-time translation services enable instant communication across language barriers. For example, translating, "Hello world, how are you today?" from English to Spanish would produce, "Hola mundo, ¿cómo estás hoy?" preserving both meaning and natural expression. Text summarization creates concise versions of longer documents while preserving key information and main ideas. There are two main approaches: extractive summarization, which selects important sentences from the original text, and abstractive summarization, which generates new summaries using natural language generation. Modern systems use BERT-based models and transformer architectures to understand document content and generate coherent summaries. This technique is essential for quickly digesting large amounts of information, from news articles and research papers to business reports and legal documents. For example, a lengthy scientific article about climate change might be summarized to, "Scientists discovered new evidence of accelerated polar ice melt, with potential impacts on global sea levels within the next decade."